Hi guys. Hope everybody's doing well. Today we are going to learn about something called an ICE table, which is just an acronym that we use to make some equilibrium calculations. Now, ICE tables are really useful to be able to predict how much of each reactant or product you're going to have at equilibrium, or to help you calculate the Kc of an equilibrium. I am going to keep this really simple just so you guys kind of get the concept, okay? So we're just going to learn the concept. We're not going to get too crazy. If you do choose to pursue AP Chemistry or chemistry in college, you're going to do a ton of these ICE tables. And I just wanted you to be able to see it and do a few problems with it just so you can kind of get the thought process of how it works in case you encounter it again in the future, okay? So I'm going to read this problem here, and then I'm going to solve it for you guys. I'm going to solve two problems, and then you're going to move on to finishing the notes guide / practice packet that you have, and then you can check the answer key. As always, I'm going to go super fast because I don't want to keep this video very long. Just feel free to pause the video at any point. Okay, so a mixture of 1.16 mole of A, 1.35 mole of B, and 0.64 mole of C is placed in a 1 liter container at a certain temperature. So these are all gases, okay? So moles over liter, the number of moles is going to be the same as the molarity, okay? Because it's the mole divided by 1 liter. At equilibrium, there are 1.59 moles of A present. Calculate Kc for this reaction. Keeping it here as A, B, and C to make life easy for you, okay? So we are going to use what's called the ICE table. So what the ICE acronym stands for is initial, change, and then equilibrium. I'm going to abbreviate here. Okay, so this is a table that we're going to draw here. We're going to have initial amounts, how much change occurs, okay? Here's my reaction as my top of my table, and the amounts that we have at equilibrium. So the problem tells us we have 1.16 moles of A to start out with, 1.35 moles of B, and 0.64 moles of C. I know that at equilibrium right here, I have 1.59 moles of A. At equilibrium, I have 1.59 moles of A, okay? So I'm going to change the color here so you can see what's happening. So what I got to figure out here is the change and then the equilibrium amounts of B and C. So 1.6 to 1.59, that means I added 0.43. That's just very simple algebra. 1.59 minus 1.16, 0.43. Okay? Now, how much did these changes? Well, because there is a mole ratio, the coefficients in here, I can use the ratios to figure out how much I gained or lost of each reactant or product, okay? So if on the reactant side we are gaining, okay, that means this reaction is weighing heavily towards the reactant side. That means on the product side I gotta lose. They always do opposite. So if I'm gaining on the reactant, I'm gonna lose on the product, or vice versa. So here, both of these are going to be subtractions. So if this is addition on the reactant, it's subtraction on the products and vice versa. Now this here between A and B here is a 1 to 2 ratio. So I got to subtract twice this amount, right? Because it's a 1 to 2 ratio. So 0.43 times 2 is 0.86. Okay? A and C, that's a 1 to 1 ratio. So I'm going to subtract 0.43. So my equilibrium amounts here are going to be 0.49, 0.21. Okay, so I have my equilibrium concentrations here. Now the Kc for this reaction. First of all, I got to write my equilibrium constant. So I'm going to have my concentration of B squared, my concentration of C, over the concentration of A. Okay, so B squared is going to be 0.49 squared times 0.21 divided by 1.59. When I put that in the calculator, my equilibrium constant is 0.031. Okay. Now here, K is less than 1, right? This number here is less than 1. So that means I favor the reactants, which makes sense. I end up with a lot more reactants. I'm gaining on the reactant side than I do on the product. Okay? So this is a way we can do more complicated problems to predict things and work backwards and do stuff like that. But this, I just want to keep it simple. Okay? I'm going to do one more problem and that's it. Okay? So 0.822 moles of SO3 is placed in 1 liter container at 600 Kelvin. 36.7% of the sulfur trioxide are decomposed when equilibrium is established. What is the value of Kc at this temperature? So again, I'm going to create my ice table. My initial amount, my change, and my amount at equilibrium. Ice. Okay? I'm not very good at drawing here, I apologize. So I start with 0.822 moles of this. And it doesn't say about me having anything else. So I'm going to put zeros there because I'm starting in the container with just this. Now sulfur trioxide is naturally going to decompose. Okay, now remember, decomposition is loss. Okay, in this case here, because I'm starting with this amount and 36.7% of it decomposed. So I'm going to have to subtract here. And then for these guys, since they do the opposite, I'm going to have to add. Now, how much am I subtracting? I'm going to change my color here so we can see the different things. So this is going to be subtraction, addition, and addition. Well, 0.822 times 0.367 equals 0.302. Okay, if I'm rounding to my 3 sig figs. So I lost 0.302. Over here, this is a 2-to-2 ratio, so it's the same thing as 1-to-1. So I'm going to gain 0.302. Now this is a 2-to-1 ratio, right? So over here, I'm going to gain half of that, which is going to be 0.151. So when I do my arithmetic here, I get 0.520, 0.302, and 0.151. Alright, so now it's just plug and chug. Kc is going to be the concentration of sulfur dioxide squared times oxygen gas over sulfur trioxide squared. I'm going to plug in my numbers, 0.302 squared times 0.151 divided by 0.520 squared, which equals 0.0509. Okay, so this K here is less than 1 as well. Okay, and it still makes sense because look, I have a lot of reactants, okay, compared to my products. And only 36% of it decomposes, which means it's still you still have more reactant here than you have the product at the end. Alright, that's how we do the ice tables. Reach out to me if you have any questions.